Hello there and welcome to this course on hyperparameter tuning with Python. My name is Valentine and I'll be your instructor for this course. So in this course, we're going to follow the following structure. So we'll get to learn about the learning objectives, what is hyperparameter tuning, why do we perform it, and also when do we apply those hyperparameter tuning techniques. We'll also get into a reading and a quiz section, and that will mean we'll go through some curated reading that we've prepared. That's what you see on the screen. And that should give you some in-depth ideas of what those hyperparameter techniques entail. Additionally, once you go through that reading, there'll be a quiz that you will need to just complete in order to just assess your understanding of those theoretical concepts pertaining to hyperparameter techniques. So once you have finished that, the next thing would be to go through the practice work, which I'll take you through. And this should take us about an hour or so. And we will go through the different hyperparameter techniques that we can work with. Additionally, we will give you challenges that you can work on yourself or work by yourself on. And the idea is that you're going to be putting into practice those techniques, as well as being able to also verify the solutions to your techniques. Those solutions to those questions that you'll get to verify them through the use of a solution notebook. Once that is done, we have a project that's majorly focused on hyperparameter tuning. It will involve the creation of machine learning models and also being able to optimize them using those steel techniques that we've covered. We've also provided some guiding notebook that should give you an idea of how you can be able to go about the solution with some assistance. So we will cover parts in that guiding notebook that enable you to just focus solely on hyperparameter tuning techniques. So for example, if you go through the notebook, you notice some of the sections for the project have been pre-filled, but only areas where you would be required to now perform machine learning as well as hyperparameter techniques would need to be filled in. So that's your focus. You would be in a position to be able to apply hyperparameter tuning techniques on a real life projects. Once that is done, you can go through a solution notebook with regards to the project, that same project that I've shown you. And the idea is that you will just get a good idea of how probably you would have approached the problem alternatively. So yeah, so for the next 2 hours, it's going to be busy. Hopefully, you get the most out of this session. And so let's get started. So starting off, what are we looking towards learning today? So we should be able to, by the end of the workshop or by the end of the course, be able to describe the concept of hyperparameter tuning in solving machine learning problems. We should be able to apply hyperparameter tuning techniques using what are called grid search, which usually would be grid search, randomized search, to be able to optimize models. These are just some of them. We will be learning of the 4 different techniques. We should also be able to differentiate between different hyperparameter techniques, as well as be able to recognize when to apply those particular techniques when it comes to optimization. Starting off, what is hyperparameter tuning techniques? So I'll just step back a bit and explain to you where hyperparameter tuning comes in. So in the process of creating machine learning models, which just generally, sometimes we would want to create machine learning models to solve problems. We might want to optimize those machine learning models. So let me even just step even far back and start from the perspective of assuming that you're a data analyst or a data scientist and you need to work on a project that helps an organization be able to automate some of the tasks that would take hours and lots of resources. And one of the solutions, one of the deliverables that you would end up creating or working on would be creating a machine learning model. And this is just simply a program that makes predictions based on some historical data that it has learned on. So So once you have created your machine learning model and it makes predictions, you might realize that the machine learning model makes mistakes, which by default, normally you would expect that. Maybe out of 10 different predictions it makes maybe 3 or 4. However, sometimes you might have some criteria such that you can only use that machine learning model once it has gotten to be really good, like you would expect it to predict out of 10 records, maybe 9 out of 10 records to be correct. And in such a situation, then when you arrive at such a situation, then you can say that the machine learning model that you're working with actually ends up doing a good job as opposed to already the traditional methods that you already have in your organization that are sort of manual. So the process of creating machine learning models, of course, it starts usually from using what are called algorithms, just complex mathematical functions. And once you have created your machine learning model from that algorithm, you train it using data. Then once you train it, you assess its performance. And once you realize the machine learning model hasn't really met your metric of success, which could be maybe 90% in the case of 9 out of 10 prediction it makes need to be true at least. When you have such a metric and you realize maybe the machine learning model that I've created only makes 8 out of 10 predictions correctly, then you might decide to perform either perform optimization techniques either by looking at the data that you're working with and ensuring that it's in the right shape. So performing what are called feature engineering techniques. We have a separate course for that. Or performing what we are going to be going through in this workshop, which is hyperparameter tuning techniques, which is now finding values for what are called hyperparameters for the machine learning models. So machine learning models normally come with sort of settings. They're called settings. Well, just for layman terms, but they're usually called hyperparameters. So each machine learning model has its own set of hyperparameters, which are just more like settings that you find the values, the correct values, combination of values for that would end up giving you the most out of that machine learning model. So for example, if I were to give you a good use case, so if we wanted to work on a machine learning model and one that a popular machine learning model would use an algorithm such as decision tree algorithm. So you might create a machine learning model that performs classification based on decision trees. And so initially you might decide to create a decision tree classifier. This is the model. And inside that particular, when you're creating it, you just want to, you can state a parameter, which is now the setting, hyperparameter, which is now the setting that we're talking about. So this is how you would create a machine learning model, a decision tree classifier or decision tree machine learning model. However, you could decide to specify the hyperparameters. Hyperparameters would come in between these two parentheses when you are creating when you're creating a machine learning model. And that is usually you could do that. But if you want to ensure that this particular machine learning model performs really well, you would need to also look up what the other hyperparameters for this particular decision tree classifier are. And you would do that by simply going to the documentation for decision tree classifier. You could just go online and on Google, just say sklearn decision tree classifier, because sklearn or scikit-learn is the library where that we are using the decision tree classifier from. So once you get there, when you get to the manual or to the actual documentation and go to the section for decision tree classifier, you'll see that there are different parameters. These are, again, they're hyperparameters, but in this context, they're just mentioned to be as parameters. And there are different parameters that you can use, which you can see inside this decision tree classifier. Let me just zoom in a bit. You have all these different parameters that you can be able to set. There's criterion, there's splitter, there's max depth, mean samples, max mean, and they all come with different values. And if you were to look at maybe criterion, and look at some more information about it, it usually comes with three different possible values. So you can set criterion to be Gini, entropy, loss, log loss, etc. We could explain this further, what these particular values mean, but that's not the interest of this workshop or this course. The idea is just to figure out how do you get the best possible combination of values for all the hyperparameters that you're using. So you might decide to specify when you're creating your decision tree classifier, maybe a few hyperparameters, such as in our situation over here, we have three different hyperparameters: max, step, mean, samples, etc., random state. But you might want to ensure that you get the right combination of values for these hyperparameters that would work well for your case. So in our situation, we might end up looking at the documentation, identifying all the hyperparameters, and then employing hyperparameter techniques to find the right values, because even some of the values are numeric in nature, such as max, leaf nodes, mean, impurity, decrease, hyperparameter. These are also they are also how should I put it? They are numeric in nature, and they can be a bit tricky to figure out manually. So that is one step, and this process again of finding those values is usually called hyperparameter tuning, which is what we are going to be going through. So I hope that just gives you a good idea of what hyperparameter just entails. So generally, by definition, hyperparameter tuning refers to optimization of hyperparameters of a model, and hyperparameters would be those adjustable parameters that you can tune in order to obtain a model with optimal performance. And that's what we're going to be doing today. The image on the far right just gives us an idea of the CRISP DM process, which is just the project management approach that we can use when working on machine learning projects or data science projects. And it starts from business understanding, data preparation, data modeling, where you create your machine learning models. You evaluate how your machine learning model performed. If it did not meet your metric of success, you go back to business understanding, or if it did, you go to the next stage, which is deployment. Now, a few just examples of hyperparameters I think we've already seen for decision trees. So for decision trees, we saw that we had quite a large number of hyperparameters. We had quite a large number: criterion, splitter, max step, mean, samples, etc. And you can always just look for the documentation for the respective classifier that you're working with to be able to determine what hyperparameters work best. Not even work best, but what hyperparameters there are for whatever algorithm that you're using to create your machine learning model for. So so generally, just going back where we the idea is that you should also have in mind that the hyperparameters for this for an algorithm would be different for another algorithm. So for example, for random forest, which is another algorithm which we can use to create machine learning models, you would find it has its own set of hyperparameters, and that just means you just need to look up. Even these are just a few. You could find more, but the idea is to find the corresponding values that give the best accuracy or the best output in terms of performance for the respective model. So the best way is usually just to go to the documentation, check out the possible values, and use those possible values in your in the creation of your machine learning model. So we also have support vector, which has these three hyperparameters, and these are the meanings of those three. In some context, you might realize that maybe you might be able to even just not necessarily perform hyperparameter tuning. You might even know by default, like, maybe for this particular scenario, when we use this data set, the machine learning model tends to perform faster. It tends to, not really faster, but it tends to work well. So sometimes you might use domain knowledge to find the respective values to that will lead to the best outcome of your machine learning model. But that's generally what we have so far. So let's continue to the next bit. there are different hyperparameter techniques. So how do we find those values that are uh, are almost what we want? So there are what are called there's what is called manual search. So you decide to input just different values based on your judgment. So you can choose those hyperparameter values and be able to use them just by simply keying them in. Alternatively, you could perform grid search or random search. These are two popular hyperparameter techniques that we can be able to work with. Which in grid search, we just entail building a model for each possible combination of all of the hyperparameter values provided. So normally you would define possible values that you think could work, and then, or even just based on maybe certain range or whatever that makes sense for you, and then you have and then you try the different combinations that you have within what you have defined, and the best possible combination from what you have defined would be one that would be selected to produce would be selected to, for, let's say, deployment or so. Random search, on the other hand, is a slight variation of just grid search, which of course in grid search you would have defined what possible hyperparameter values you should check, and it could be for maybe one hyperparameter. It could be maybe for something like n estimators, number of decision trees in the forest. You might decide to do maybe 5, 10, 20. Is what you want to try for that estimators, and then the same case you'd also define the ones that you want to try for max depth, maybe 20, 21, 22, depending on what makes sense for you. And then once you do that, when you perform grid search, you would actually perform all of them. You would sequentially, like, you try the different combinations that you have for hyperparameters, and you would get the best outcome possible. For random search, it's usually slightly different, but yes, you use the same approach where you have already defined the possible hyperparameters that you want to work with. But instead of searching the entire grid from start to the very end possible combination, the testing of the different hyperparameter, the selection of different hyperparameters or combination usually just happens at random, not just from the start to the very end. So that is usually something that you can be able to use. Lastly, there's Bayesian optimization, which normally works differently from grid search, random search, and manual search, in that it uses what is called Bayesian optimization, or Bayesian techniques, to be able to get the optimal set of parameters. And it usually takes into account of just hyperparameter combinations that it has seen. So it just uses it checks whether did the previous hyperparameters that it tested yield a better result or a poor result. If it's a better result, then it tries to ensure that the next hyperparameters that would be used in just figuring out what works best for that machine learning model is actually better than the previous one. So it does that through the use of what is called Bayesian reasoning. So why is hyperparameter tuning important? So it's important if you want to optimize your model performance. So if you haven't really met your metric of success, which usually depends on whatever metric or evaluation metric that you've selected, then you would perform hyperparameter tuning techniques. If you also want to use your resources effectively in order to get the most out of those resources, then you can perform hyperparameter tuning techniques. If you also want to ensure that you tailor your machine learning model to whatever specific domain that you're working with, and especially the data that you're working with, then you can be able to perform hyperparameter techniques. And these are just some areas of why hyperparameter techniques are important. When performance matters, that's when you should apply. Just a recap: when to apply hyperparameter techniques, when performance matters, when data changes over time. So if your data set evolves and changes over time, so you might need every time to adapt your model to new data characteristics. So you need to ensure that your model performs optimally. You need, again, to perform hyperparameter techniques, and also when working on a competitive task. So for example, if you're working on a machine learning competition, so hyperparameter tuning can be important because the idea that the metric of success is usually quite high to get the best possible accuracy or the best possible performance of your machine learning model. All right, so at this particular point in time, I would like to ask you to go through the quiz, which will be in the next section. So the idea is now to go through the reading, this reading, which will cover just different concepts pertaining to hyperparameters, but now a bit more in depth. Once you have done that, go through the quiz, which we have also provided to just solidify or to consolidate all the information that you have gotten. It's a self-paced quiz. You can pause the video after this, and then we can come back and we can continue to work on the practice work. All right, so once you have gone through the quiz, the next thing that we're going to do is to go through the practice work. So you should open the notebook that we've shared. So by the way, the resources that you will find that we have shared on you right now on this particular course, you can be able to access them depending on the platform that you're accessing this course on. So if it's on YouTube, that will take you to the Afterwork platform where you would need to be able to, you can download the resource, this resource for learning. But at the same time, if you want to but this resource for practice work is actually you'll find a sample notebook that has just only examples. But if you want extensive resources, including the reading and the quiz, you could always consider becoming an Afterwork member if you come from the YouTube side. But on other platforms that from which you're watching this from or doing this course from, you should have those resources readily available. So you could now just go to the practice notebook and then we can continue from there. All right, moving on to the practice notebook. So this notebook is just a document that we can use for performing data analysis or even creating our models. Normally, machine learning engineers or data scientists or data analysts would use such. So the first thing that we need to do once we get here is to save this document and save it in Drive save a copy in Drive so that you have access to it later onwards in case you just decide to continue working or to just refer back to some of the examples and challenges that are in the book in this particular notebook and just do that, file, then save a copy in Drive. Once you have done that, the next thing that you need to do is to connect this notebook to Google servers. This notebook is hosted on Google Drive. Google Drive has an application that allows us to be able to work with this notebook or just notebooks generally, which is called, and that application is called Google Colab. So to be able to connect our notebooks and be able to run code that resides in our notebooks, we need Google Colab. We need to connect our notebook. Once we have done that, we need to import the prerequisites. So there are many other prerequisites that we will need, like sklearn and some others, or scikit-learn. But for now, we are going to import these two libraries. If you get this prompt, just know that you need to save a copy in Drive. I don't want to save a copy in Drive. Just want to continue. Just giving you, I don't want any changes. So that's why I just say it run anyway. So import pandas for data manipulation, import NumPy to perform scientific computation. Two libraries important for just data preparation purposes. So the first technique that we'll go through is manual search, there's grid search, there's random search, there's also Bayesian optimization. Let's open up manual search and go through the example that we need to go through. All right, so starting off, we'll go through this particular example. Well, first of all, let's go through the question. Will John, 40 years old, with salary 2,500 buy a car? So the first thing that we need to do is to load this data set that will allow us to be able to optimize, to build our model and also be able to later onwards perform hyperparameter techniques. So I'm going to create a new cell, which you'll see code cell. And then I'll copy this. I just want to preview the data set so that we have a good idea. I should have done this earlier before, but yeah, so let's just do this. Socio df, and I said head. You can also do this. You can also pause and do this. Just preview the data set and how it looks. So this is how our data set looks. We have user ID, gender, age, estimated salary, and purchased. So what we want to work with is actually gender, age, and estimated salary, which will be part of the features within our data set. And we have purchased, which will be a variable of interest or a target variable or label. We'll drop user ID. If you find that, by the way, if you find this a bit if you find some of the terms that I'm talking about a bit complex, just refer to the regression analysis or classification analysis courses. Um, we've also done them before. You'll find them on whatever platform that you're accessing this course from. You'll find them there. Those are much more, they're more prerequisites courses for this particular course. Either regression analysis, classification analysis courses, or even ensemble learning. Once you have done those three, then some of the terms that will be in this particular workshop or this course will feel a bit easy. So once we have done that, the next thing that we need to do, so we've understood this is just a data set that contains respondents for different users or customers who have bought cars before or have not bought cars before. So these are just information. It could be based on maybe um, could be maybe some institution that sells cars, but it wants to also sell cars to its own employees, and they have this data as well. So we already know that that's our data set. So what we're going to do is perform data preparation, perform an encoding technique. We want to prepare our features, that's gender, age, and estimated salary for training. We'll notice that gender has categorical values, and we want to ensure that all the machine learning models that we will test or the machine learning model that we'll use is able to also take into consideration of this column. So we need to change this to have, for male, we want to have the value 1, and for female, we want to have it 0. So that's what we tend to do in this line. We specify the column that we want to replace values for, which is gender. And then we use numpy in the where function from numpy to be able to perform that replacement of, for the gender column, where we have male, substitute that with 1, and female, again, substitute or replace that with 0. And that will be what will happen. Once we have done that, the next thing that we need to do is to select the predictor or the features. The features that we are working with is gender, age, estimated salary, and purchased. This is the target variable. Actually, this is not a feature. This is the or label target variable. So we have 3: gender, age, and estimated salary. To select them, we use positions. So this is position 1. The user ID, we don't need this. It doesn't give us any important data for this analysis. So we'll drop this. So we don't select this. So this is usually position 0, then position 1, 2, 3. Yeah, so we select the um, the values for that column. We specify the data frame or the data frame, the data set we're working with. Then use the iloc method. We want to select all the records, comma, then we specify for which columns that we want and specify the positions for those columns. Then we say dot values to be able to select the values and store those independent values or features in X. The same case we do for the purchased column. We do that, but we specify its position 4, and we store its values in Y. Once we do that, we split our data set using the train test split data set. But once we have imported that function, not data set, but a function, train test split function, and how to do that, to be able to split our data set. We want to split our data set into a training data set and a test data set. And again, we also want to ensure we also split those data sets to have just the predictor variables, that's the features, as well as the labels separately for both data sets. Training the machine learning models that it learns how to predict, we'll use the training data set. And for the testing of the performance of our machine learning model, we will use the test set. However, to split now those two training and test sets into 4. That's features or independent variables for train set and independent variables for test set, and dependent variable label or target for the training set, and the same case for target for the test set. We create these 4 variables. So xtrain will contain the features for the training set. Xtest will xtrain, that is, xtest will contain the features for the test set. Ytrain will contain the features for the it will contain the target or values for the y column. That's the target column. In the same case, y test will also contain values for the test set. And train, and then we do that. So we use the train split test split function to be able to create the 4 data sets. We pass inside this function x, which is the features for the entire data set. In the same case for y, the y values. And then we specify how big we want the test data set. We want it to be 25%. We specify it at 0.25. So that means 0.75 will be now the training set. And we set to random state to equal to 42, because we want to ensure that we have reproducible results. Like if someone were to get this particular data set and they wanted to reproduce the results as we did in the same data sets, then we can be able to they can be able to do that. Otherwise, they will keep on getting just different outcomes. Again, once we have done that, we have those 4 data sets. We decide to transform the independent variables or the features, so that we don't have one particular column have a greater impact on the performance of our model. So we decide to make sure that all the features that we are working with are within one certain range, from 0 to 1, or just ensuring that their magnitude of those particular variables don't affect the performance greatly of that model. So we perform feature scaling using standard scaler. Once we have done that, which then let me run this to be able to do all of that together. Once we have done that, we now import our algorithm, decision tree classifier, the one that we're going to be creating with, and then we create our model. We set random state to 42. Normally for decision trees, you would specify that. And then once we have created that machine learning model, which is now, or we can reference it through the decision classifier, we've trained our model using the fit method, and we pass the features for the trained dataset and the values for the trained dataset. That's the target variable, the target variable or the label, and we train our model through that data. Then we use our model to make predictions, and we check the predictions, or we check the performance of our model by simply generating a classification report, confusion matrix, and accuracy score. So let me train our model, which will do that. This step it will be the same, but now we'll just be applying just hyperparameter tuning techniques later. Here we've only set this as the hyperparameter tuning technique, but we will come to later set others. So we just want to create a base to work with. So we have now seen our prediction. So an accuracy metric of 0.84. This is our confusion matrix. And most of the times we want this to be more than what you have here. The same case, this number to be more than what you have here. And generally our machine learning model is okay. 0.84 would be fairly okay. Then now, assuming that this is now our baseline, so we have now something to compare our hyperparameter tuning, the results that we'll get after we performed hyperparameter tuning. So we will create another model. And again, replace the original one. We create another model, but now we specify just manually the the values for the two hyperparameters, actually three. Max depth, mean samples, random state just stays the same. Train our model again, and then we print out those accuracy metrics. And just by simply specifying the max depth to be 2 and mean samples to be 50, you can see that we have improved even our accuracy score from an 84 to a 90, or 0.9 to from 0.84 to 0.9, and also the classification matrix has also values which are way different. So you can remember here we had 28, then 9. Here we have 36, then 1. So generally, you can see that we have essentially gotten to have performed manual search, which is just we decided to input our own values, and we were able to improve the performance of our machine learning model. All right, so you can just run all of that, try that by yourself, and also they just answer this question: can you get a better accuracy? You can even consider going to that, reading the decision tree one, and choosing different hyperparameters and choosing just different values, and see what that has an effect on the actual performance at the very end. And you can also read more about hyperparameter for decision trees in the reading that we have shared. And once you have done that, now go through the challenge and verify your challenge through the solution notebook that we have provided here. All right, moving on, the next thing that we're going to go through is grid search. In grid search, we actually are going to go through the same process again of, I think we've already created, we won't even actually go through the data preparation steps. What we are going to do is to recreate our model. So we will recreate our decision tree classifier without now specifying the hyperparameters. And then we initially, but now we want to we perform grid search. And normally we would create what is called a grid. That grid would just be a container that would contain just the combination of values that we want to test out for different hyperparameters. So we'll define our grid, and we would do that using the dictionary, which we can see here. And we specify for each key value, we would specify the key to be the hyperparameter, and also the value of that key to be now the possible values that we want to try for that max, for that hyperparameter. So for an instance here, we have these values that we have set. So we want to try this combination 2, 10, 2, 20, 3, 30, and check out which possible combination of these hyperparameter yields the best outcome, as opposed to just trying these manually. So we just define this in a sort of a grid, and we can have more key values, as many as there are hyperparameters in that, with regards to that particular machine learning model. So let's run that. Once we have run that, the next thing that we need to do is, now once we have defined our grid and the parameters that we want to test out, the next thing that we normally do is to use what is called the grid search CV object, which will basically help us be able to identify those particular hyperparameters that will enable us to have the best possible hyperparameter, the best possible performance. So we import grid search CV. We'll store that in this particular instance. So we create an object of grid search CV, and then inside, when we are defining grid search CV, we define the machine learning model in question, which is the estimator. We define it. We want it to use the decision tree classifier, which you see here, and then we define the a dictionary that we had earlier onward set, that contains the key values, or that correspond again to the hyperparameters, as well as the possible values that we want to look for. We want to use the accuracy metric for measuring the performance, for checking how well the performance, how well the model performs. We will be checking which of the combination of values gives us or yields the best results. Then we set this parameter CV to correspond to what are called number of folds, which is 5. That's a bit more. It's like a bit more of a complex parameter, but it's one that we would need in our case. And then we specify the njobs parameter to be -1, which will just give us the available computing power that we need. So generally, but you could have a look at the grid search CV documentation to find more information about what those parameters mean. So we instantiate that object and we run that, and then we now train our we use the training data set features as well as the target values of the training data set to determine which of those hyperparameter values work best for the decision tree classifier that we have. And we run that, we train that, and we should be able to have identified those parameters. And then we check the best parameters by simply using the best params attribute or property to of 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 um of 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 the grid search CV object that we had created earlier, and then we should be able to see that max depth 3 and mean samples leaf of 10 actually give us the best possible outcome. And to be able to see this is this is just the best, but now to be able to obtain the accuracy, we can be able to just simply use the best score attribute for that. And this is what you can see the outcome of our result, 0.096666, which is slightly better than what we had gotten here, 0.9. We hadn't gotten any decimals in that, but this is slightly better. And that's it, generally, how you implement grid search. Now, work on the challenge, verify your solution, and then we'll continue to the next one. Now, moving on, the next technique is called random search. We'll go through almost a similar process to random search, only that we will implement random search differently. So let's recreate again our decision tree classifier, the one that we want to work with, without any specifying any models or any hyperparameters. Just random forest is okay. Then the next thing that we need to do is to define again the dictionary that we need to perform random search on. But now this time round, you could actually specify what we did, like the lists. We could specify the values that we have there. However, in some other instances, especially for the numerical the hyperparameters that need a numerical value, we can use another function, sp.randint, that will just generally be able to give us some random integers between what we have specified, between 1 and 50, to be able to do that. And it will give us generally the best performing which we can be able to use to be able to determine the best performing hyperparameters. So let's run that. We actually imported that from SciPy. This is another library that we can work with. Once we have done that, we will now import another another class called randomized search CV, which is different from grid search. And this will implement random search technique while using still the given parameters that we want to search for. So let's run that to be able to do that. We provided a link for just getting more information about that particular random search CV class there, and you can be able to also find what its parameters mean. So once we have done that, we fit our data, we train our data set, and then we find the best possible parameters. We check the best possible parameters, which is 3, 24, which slightly different from what we had. 3 mean sample leaf, 10, slightly different. Let's see whether we are going to get a better outcome, which it's actually the same outcome. It's only that we looked for the values of mean samples leaf randomly, as opposed to us being able to have specified a grid. And yeah, so that's it. Can you get a better accuracy? Just refer to the decision tree documentation, choose additional hyperparameters, and set the hyperparameter values to the random search space, which is here. And then, try and see whether you're going to get a better accuracy. Work on the challenge, and once you're done, you've done that, work on the solution. Check your challenge and check the solution that you've come up with, and verify whether it was actually what was intended using the solution notebook. And then we'll continue. All right, moving on. The next step that we're going to be going through is Bayesian optimization. So this is the last technique that we will go through. So starting off, we'll still again, what do we do? I think what we need to do is to define the all right, I was just checking whether we need to again recreate our classifier, so we may not necessarily need to do that. So the first thing that we need to do when it comes to Bayesian optimization, when we are implementing this technique, we normally do three things. We set up what is called a space dictionary, and in this space we create a probability distribution for each of the hyperparameters that we want to use. Then we again set up what is called an objective function, using that particular classifier or regressor or machine learning model. Then we run the Bayesian optimizer to determine those hyperparameters that we want. So the first thing that we need to do is just to import what is called the Hyperopt library, which will help us perform Bayesian optimization. You can have a look at that particular link that we've shared for that. And then once we have done that, we set up the space dictionary. So we had mentioned that the first thing that we do is to set up a space dictionary, which we do, which is just contain almost similar almost like a similar grid that we had defined earlier for either grid search or random search. It's a similar dictionary, but now in our case we specify the parameters that we want to try for. But again, we also decide to use the Hyperopt library to be able to define the possible values that we want to search for using now Bayesian optimization. Once we use the h dot q uniform function to be able to specify those values that we want to set to look for. So once we have done that, we then later onward set up our objective function, which you can see there. And the objective function would need to have we would need to specify the classifier inside it, and also we would need to specify the accuracy, or which generally be the output of the performance. So what we would use to identify which of the hyperparameters perform best. So in our case over here for the classifier, we would set the different possible hyperparameters that we want, as well as reference the space that we need. And you can also do you can also add as many hyperparameters as you want. And then once we have done that, we return a dictionary that will contain our accuracy, or the metric of the evaluation metric, as well as the status to suggest that we have actually been able to implement it. Then we run our Bayesian optimizer. So we use the fmin from Hyperopt. So fmin function, or an object we create an fmin object from Hyperopt, and we set now its parameters to the values that are needed for Bayesian optimization. So the first thing that we need is to set the objective function. The next thing that we need to do is to set the space that we had set here. And then we need to also suggest the algorithm that we want to use for searching of those hyperparameters. We want also to specify the number of iterations to be able to perform in order to look for those particular hyperparameters. And lastly, we set the random state, which is a familiar parameter. But in our case here, we do it differently from what we would do in other areas in our code. This is how we set random state for reproducibility so that other persons may be able to reproduce what we get in terms of the same outcomes. And then lastly, we print out our outcome. Whoops, we have an issue here somewhere. Okay, so I think the reason why we're getting this error is because you have numpy, random state, blah, blah. So I think we need to remove this. I'll update that in the notebook. So we need to remove this. I think fmin does that internally. So we will just remove that comment so that we have that. And also we need to have ints this to be an integer. So this to also perform some conversion. Don't worry about that error. I'll have resolved it by the time you're accessing this course. So if we run this, we should be able to get our output, which we can see that this is the best hyperparameter that for these values for this particular case that we could get. But we can run this again and we get a different value. So we can get this and this. So every time we get a different value technically as a result of that. But now the issue that we are getting is that every now and then we keep on getting some different hyperparameters. So we need to make this reproducible. But we could actually so we could still use the same value for hyperparameters. So let me see. Okay, it doesn't. I think it's R states args or something of that sort. So yes, so R states that. So again, I'll have updated this in your notebook. So R states then np random dot default 42, and that should give us the same number of the same hyperparameters every now and then. So that's 360. So if I run this again, I should be able to get 360, then this particular number. Yes, so I should be able to get the same hyperparameters with this particular accuracy that you find there. Yeah, so for these particular parameters, we can access them as shown. And we have a max step of 360, mean sampling of 0.097, etc. And we can again perform our classification using that model. Okay, so decision tree classifier. Getting this. Must be an integer, so we need to convert this into an integer. And 360, the reason why we're getting that's max depth. This needs to be an integer. It's giving us 360.0, which is technical. It's a float, but we need an integer. We have done that. Then we can decide to evaluate the performance, which actually evaluates to 0.92. And voila, we have a machine learning model. So initially we started off with 0.84. If you remember, the same model we did get when we performed, we just worked with what we had. We did not specify anything. We started with 0.84. Then we did manual search. We got 0.9. Then we went to grid search. And for grid search, we got 0.91 because 0.906 just equates to 1 in full. I think the same case we did here. We also got 0.91 using random search and random grid search. But then when we got to Bayesian optimization, we were able to see that we got to 0.92, which is good. And yeah, so I think you can even try different hyperparameter values and see what works. So the next thing that we're going to do is to just work on the challenge that's about Bayesian optimization. and then check on the solution the solution notebook that we have for that. And once you have done that, um, come back and we'll continue with the project. So now we have this project that you can work on hyperparameter tuning with Python. The idea is that you're going to go through the steps that involve performing hyperparameter tuning techniques. You'll initially be required to create a machine learning model, and then later apply different hyperparameter tuning techniques in order to ensure that you have gotten a best performing model. So we've also provided a guiding notebook, which you will find there. Just click on that link and it should take you to this particular page. We have already curated content for the sections that are not covered in this workshop on this course. So you could always refer to, if you really, really want to learn more about all the concepts that we have gone through this, that have been used in this particular notebook. There are other courses that we have that could provide you that information. So you could look into um, data visualization with Matplotlib, as well as Seaborn, data analysis with Python, as well as data wrangling with Python. Those courses should prepare you should prepare you to be able to go through the entire notebook with ease. But you can still run the code. It takes you through the entire process for initially preparing yourself for this workshop. I also see that there's an feature engineering section that you need to go through. You can still actually go through another workshop called feature engineering with Python. But if you're not really sure, you could always refer. If you're not really sure, you could always refer again to the solution notebook for that particular section to be able to go through that section. But once you have done that, you can go through now machine learning modeling, or the process of creating a machine learning model, and then you can be able to apply those techniques that we have covered so far. And once you're done with this particular workshop, I think the next workshop, probably, as I had mentioned, maybe you could looking into, is feature engineering. Once you have done that, you could also look into possibly performing text analysis, working with text data, and ensuring that you're also able to perform machine learning with those particular techniques. We also have so many other courses that you might want to go through, and the idea is that you become a better person having achieved those skills and be able to solve for different kinds of problems that would be thrown your way. So all the best in your learning journey, and if you have any questions, feel free to ask in the chat or comment section of whatever platform that you're accessing this content from, and all the best in your journey. See you in the next course.